Respected all, I'm here to give my presentation on fog computing based Internet of Health Things for healthcare in pandemics. I will begin my presentation with an introduction to Internet of Health Things and fog computing. And then I will introduce the concept of fog computing based IoHT. I will also discuss in brief about the literature review, which will mainly consist of two research papers. I will conclude the presentation with the proposed problem statement and objectives. The Internet of Things refers to the connection of embedded devices within an existing internet infrastructure in a computing environment. An IoT becomes Internet of Health Things when devices embedded facilitate the exchange and processing of health data collected using the body area network, which is made up of all the sensors used to collect health parameters. Fog computing is a model in which data processing and applications are concentrated in the devices at the network edge rather than the cloud. This makes fog computing leverage the local knowledge and is more suitable for real-time applications. Any devices such as router, server, or a switch can act as a fog device if it can process data and generate the results. Instead of opting for traditional cloud computing, which has issues like processing of voluminous data, network congestion, delay in access, and connection interruption, fog computing model overcome all these issues as it is more distributed. Further, it also overcomes the limitation of IoT devices which need energy conservation and have limited processing capabilities. A fog computing based IoHT consists of the following components: body area network, a mobile device like smartphone, fog devices in the form of access points or roadside units, and the cloud. Now I will discuss the following two research papers related to the successful implementation of fog-based IoHT. In a weighted majority game theory based energy efficient delay sensitive fog IoHT, the proposed framework consists of three tiers. The health data is collected at level 1, transmission and processing is done by the fog device at level 2, and cloud computation at level 3. For making a decision whether the data computation will be done at the mobile device or will be transmitted to the nearby fog device, the following two parameters are compared, namely dpdev, which is the delay in processing the data at the mobile device itself, versus d-offload, the delay in computing the data at the fog device. The minimum of these two is considered. This decision of offloading the data to the fog device is crucial and taken frequently by the user's mobile device as soon as it receives data from the ban, as shown in the following state diagram. In case the data needs to be offloaded to the fog device, we first need to select the nearby fog device. This is done using the weighted majority algorithm. Further, if the data is found to be abnormal, then it is uploaded to the cloud server for further analysis. In the indoor region, femto access points, cloudlets, or small self-cloud enhanced e-nodes can be used for preliminary data processing as fog devices. Wi-Fi can also be used to connect the smartphones to fog devices. For outdoor regions, RSUs can provide internet access while traveling in vehicles. They can also act as fog devices. Portable fematocells can also perform preliminary data processing and can act as fog devices. Now I will present a brief overview of weighted majority algorithm used in the selection of fog devices or the access point or roadside unit. Given a number of devices, the weighted majority algorithm requires a payoff matrix as an input and computes the utility function for the set of high majority devices. The device with the highest utility value is finally selected. For access point, the payoff matrix includes the distance and the load of each access point device from the mobile device, and higher majority device having minimum distance and low load is selected. While fog device payoff metrics include the number of requests processed and the resource availability, with the higher majority assigned to one with minimum number of requests processed and has sufficient resource availability. Lastly, for RSU, it is the distance and the signal strength which are considered for selection. Concluding the discussion on this paper, by some empirical findings. The network scenario was simulated on CallNet, and it was found that the average delay, jitter, and energy conservation were reduced by 15%, 20%, and 15% respectively as compared to the cloud only healthcare system. Next, I will discuss about IoHT for personalized healthcare using integrated edge fog cloud network. The proposed model consists of three steps. Step 1, sensor node collect data categorically. Step 2, mobile device sends the data to fog device with contextual and geolocation information. Step 3, mobility pattern detection and storage inside the cloud servers for further action. As seen in the given figure below, the mobile device collects data from WAN and can send it to multiple fog devices, which can analyze the data in parallel. If the data found is abnormal, it is sent to an aggregating fog device, which compiles the data and cloud server. Now, for the third step of the model, mobility pattern is computed in the cloud using multi-layer mobility pattern graph. For this, we define the following terms: GPS trajectory, a sequence of latitude, longitude, and timestamps. The road network R, which is a graph of road intersection as vertices and roads as edges, and trajectory segment, which is a sequence of GPS positions between two stay points. Now, the multi-layer mobility pattern graph consists of three layers. Layer 1, the road network itself. Layer 2, the point of interest. And layer 3, the GPS data of moving agents. These three layers are interdependent and are related through the function M. To form the topmost layer, clustering is performed to group movement patterns over different timescales using a similarity matrix that has C connected components. The similarity function sinCS is very similar to the least common subsequence function, distance function, which is used among different trajectory traces. In the next step, optimal path is predicted based on the present traffic state and the present location of the moving agent. A variant of GAN is used to predict the optimal path. The major reason for using GAN is its capability to make prediction even in case of noisy or low availability of real-time data without any overfitting issues. Hence, authors have preferred to use GAN over the widely popular neural networks, which might even get stuck into a local minima. The model successfully predicts the traffic density and suggests optimal path with reduced travel time. It was implemented using three Raspberry Pis as fog devices and an Amazon EC2 cloud service. And the simulated results prove that the framework outperformed existing cloud only healthcare solution by 28% less delay and 27% less energy consumption. Here are some other related works which were seen during my study of the following two papers. Based on the above study, we have formulated the problem statement. To design an energy efficient delay sensitive integrated fog IoHT for prediction of pandemic scenarios, the range of the healthcare parameters considered can be temperature, oxygen level, glucose, and BP. And the following are some possible objectives: to design a fog based health model to reduce latency, network usage, and cost incurred at the cloud, to select suitable wearable devices for the collection of health parameters, to test the design model using a simulator, to implement the proposed model over hardware and test its efficacy. Thank you.